In this example, we're going to find another surface integral. We're going to integrate the function over the given surface. So the function g of x, y, z is equal to z minus x. And we're going to integrate over the portion of the graph of z equals x plus y squared, which is above this triangle in the xy plane. So the triangle has these vertices, 0, 0, 0, the origin, 0, 1, 0, and 1, 1, 0. The first thing we want to think about is how is our function defined? Because we have three different formulas. So if I wanted to write this as f of x, y, z, that would be f of x, y, z equals x plus y squared minus z equals 0. So we're going to say that this is defined implicitly. And if my surface is defined implicitly, we use this formula. So we need to calculate the gradient of f, and gradient of f dot p. Remember, this p vector is going to be orthogonal to our region. And orthogonal to our region in this situation would be coming straight up. We're going to use the k vector. So now that we know how this is defined, the first thing we're going to do is find gradient of f. The gradient of my f here, we have I plus 2y j minus k. So this is just found by taking the partial with respect to x, with respect to y, with respect to z of each of those components. Then we need the magnitude of the gradient, which gives me 1 squared plus 2y quantity squared plus negative 1 squared, or the square root of 2 plus 4y squared. As we said, we were going to let this p vector be k. So now we need to find the magnitude of del f, or the gradient of f, dotted with the k vector. So third step here is the magnitude of gradient of f dotted with k. Gradient of f, so that's the magnitude. We had 1, 2y, negative 1, and that's going to be dotted with k, which is 0, 0, 1. That dot product gives us negative 1, and the magnitude of negative 1 is 1. So my value up here, I'm going to have that gradient of f, the magnitude of that, which was the square root of 2 plus 4y squared, divided by 1. So this value, we know what that value is. We've got our function in terms of x, y, and z. So my fourth step here, I'm going to say the gradient of f, magnitude divided by the magnitude of the gradient of f, dotted with the k vector, was the square root of 2 plus 4y squared. And we can simplify that and say root 2 times 1 plus 2y squared. So now, in order to integrate and have this be a double integral in terms of x and y, I need to make sure that my g function is only in terms of x and y. G was given to be z minus x, but we know how to define z in terms of x and y, so I can plug that in right here. So fifth, g of x and y, that is going to be z. Well, z, again, z is x plus y squared. So I've got x plus y squared minus x. My function, g of xy, is y squared. So my double integral, my surface integral, over the region, we're going to have g of xy, which is y squared, times this value we found up here, which is root 2 and root 1 plus 2y squared dA. So now we need to figure out our bounds. My bounds are going to be in terms of x and y. And we need to be careful when we're thinking about this. Traveling along the x-axis from x equals 0 to x equals 1, we could say, well, x equals 0, what would be the function that we touch? X equals 0 to the line x equals y. This line is the identity. And then my y values would subsequently go from 0 to 1. So it makes more sense to integrate with respect to x first. So in this case, we've got the integral y equals 0, y equals 1, x equals 0, x equals y. Got the square root of 2, y squared, and the square root of 1 minus 2y squared. That would be dx dy. And it also makes more sense to integrate with respect to x first because there are no x's in our function, or rather our integrand. So I'll pull that root 2 out in front. I've got y equals 0, y equals 1. And integrating this, I'm just going to get x, y squared, the square root of 1 plus 2y squared. We need to evaluate that from x equals y to x equals 0, then we'll still have to integrate with respect to y. So plugging in y, I'm going to get y cubed. Plugging in 0, this term is just going to 0 out. So I have the square root of 2. We've got 0 to 1 of y cubed. I'll go ahead and rewrite that as a 1/2 power. So I've got 1 plus 2y squared to the 1/2 dy. Now, integrating this isn't too bad, but we do have to run through 2 substitutions, right? I can't let this just be u because I've got this, multi-piece function in here. So what I'm going to do is I'm going to let u equal y squared. So when I do this, I'm going to have 1 plus 2u to the 1/2. And this is the same as y squared times y. So here's that y dy. So let me rewrite this before we do our substitution. I've got root 2, 0 to 1, and my bounds, of course, you can see here aren't going to change. But I have y squared times y times 1 plus 2y squared to the 1/2 dy. And you can see that's going to give me root 2. My bounds, they didn't change, but 0 to 1. So y squared is equal to u. Y dy is equal to 1/2 du. And then I'm left with 1 plus 2y squared. That's 2u to the 1/2. So that was a fun little substitution. Again, y dy, that gave me this 1/2 du. And then I have 2y squared, so I plug u in twice. So now we'll do another u substitution. And since we already have u, I'm going to do a w substitution. I'm going to say let w equal 2u plus 1. And then dw du is 2, or rather 1/2 dw equals du. And then my bounds, w equals 2 times 1 plus 1 is 3. W equals 2 times 0 plus 1 is 1. So this is root 2 over 2. We've got times 1/2 the integral from 1 to 3 of u. So there's still a u. I didn't figure that out yet. So there's a u, and then 2u plus 1 That is w to the 1/2 dw. So we still have a u in there, but that's pretty easy for us to figure out because we can say, well, w minus 1 over 2 is equal to u. So this piece right here is now w minus 1 over 2, which leaves me with in front root 2 over 8. 1 to 3, we have w minus 1 and w to the 1/2 power dw. Now this is easy for us to distribute and then integrate. So root 2 over 8, 1 to 3, I've got w to the 3/2 minus w to the 1/2 dw. And that's root 2 over 8. I have 5/2, so 2/5 w to the 5/2 minus, that's 3/2, so 2/3 w to the 3/2 evaluated from 3 to 1. And of course, at this point, the algebra is just busy work. And I have written out our algebra steps for here. We plug in 3, we plug in 1, we simplify and get some values. There's some subtraction and reduction. 18/5 minus 10/5 gives us 8/5 root 3. We can factor out a 4, which turns that to a 2. And basically, we end up with 6 root 6 minus root 2 over 30. And that is how we integrate a surface integral or a continuous function across a surface.